Thank you. Okay, we have aromaticity, which is a green, yeah, and we have a white one. Any questions thus far about aromaticity?
How do we know if a cyclic hydrocarbon is planar or not planar?
Okay, you can build a model.
Right?
Okay.
Is there a way other than that?
You can't always tell by looking at it on
Okay.
paper. Okay, we'll talk about a couple of examples of where it's not, but actually one of the first things you have to determine. Because if it ain't planar, none of this MO diagram stuff that we did applies. Okay, and what's the last one we looked at? We looked at, can we name that compound? Okay, we did MO diagrams last time, yeah? And we were looking at compound here. Cyclooctatetraene. Cyclo-ring, octa-8, tetraene, 4 enes. Just because we can name it that, is it really just 4 alkenes? Or is it something special that we call aromaticity? Full cyclic conjugation, which leads to a very unique stability. Well, I told you, Huckel's rule actually predicts it to be what? Huckel's rule predicts it to be anti-aromatic. It's a 4N number where N is 2. 4N numbers, 4, 8, 12, 16, 20. Okay? Is it anti-aromatic? Well, actually not. It's actually quite stable compound. Now, it's not aromatic, because to be aromatic, it has to have 4N plus 2 electrons. And that is if N is 0, 2, and then if N is 1, 6, if N is 2 is 10, 14, 18. Okay? Those numbers. Because only with those numbers are you going to have all electrons paired when you do MO. Huckel will recognize that. Certainly not aromatic. But is it anti-aromatic? And the answer is actually no, because it's not planar. Does a compound want to be anti-aromatic? No, it hates it. Can a compound change its hybridization or its conformation or anything to avoid high energy? Yes. If this was planar, it would be like that. Okay? Planar. Flat on the board. Okay? The board's here, flat on the board. Anti-aromatic. Instead, this compound goes. Whew. Do you feel the relief now? Now it's no longer planar. 2 in the plane, 4 in the plane, 4 forward. That's not planar. Okay, it will no longer sit. And since it's no longer planar, the MO diagram theory leading it to be anti-aromatic no longer applies. This compound is just 4 alkenes in a ring. Okay? So, what type of, where would you expect the H's at? All H's are equivalent around this ring still. Where would you expect them at in the NMR? Proton NMR. Alkene region or aromatic region? Alkene region. I just told you it's just 4 alkenes. Okay? What about a heat of hydrogenation? What about X, Y, and Z? We talked about experimental evidence. Okay? So you should think about that. Because ultimately the original question was, how do you know? You can build models. But how do you know real life? Get some data on it. If the HNMR looks like alkenes, then maybe it's not aromatic or anti-aromatic. There's actually very few anti-aromatic compounds in the world, because many of them will avoid it somehow. They'll be like, whoa, I don't want to do that. By the way, did you also see that another reason for it to go puckered? Look at this bond angle here. That's way greater than 120. And look when I do this. It just naturally, even the model just naturally wants to be like that. And now the bond angles between these 2 trigonal planar carbons are more like 120. So that also relieves bond strength. It don't want to be planar. Okay? We'll see a couple more examples. So Huckel's rule is based on it being planar. Conversely, any anti-aromatic or aromatic compound is planar. Unless they avoid it. What about an aromatic compound? Is it going to want to avoid being planar? No, aromatic is good. So Consequently, all aromatic compounds are planar. Why do they have to be? Well, because every p orbital in the ring has to be overlapping. Now look at here. If these two are here, that's just an alkene. You got 2 pi bonds, 2 p orbitals, 1 pi bond. If it was planar, imagine I had 8 pencils and they're all sticking up. There's 2. There, well, I can do 4, but I can't do the other because I need 2 more hands. Imagine 2 there, okay, and they're all sticking straight up and they're all interacting. Okay? Well, I'm going to do the 2 next door. Okay? When this thing puckers, now those 2 are like that, these 2 are like this now. And you see they're no longer interacting. If this thing goes planar, now it straightens back up. And these 2 would be straight up. So you can get a model, you can look at that, and just know that for the p orbitals to all interact, the system has to be planar for them to all be, they're all perpendicular to that plane. Okay? So if it's not planar, it makes the p orbitals go no longer interacting. All right? So why the discrepancy? Because this compound's not really planar. Just a compound with 4 isolated alkenes. Okay, what do we do for these? Aromatic, anti-aromatic? Basically, what do you call this compound? Aromatic? No. Anti-aromatic? No. This would be called non-aromatic. This is a non-aromatic compound. Just like water is non-aromatic. Or propene is non-aromatic. Or ethanol is non-aromatic. It's a non-aromatic compound. So non-aromatic would be our sort of third category where it's really default. Neither are the other 2. It's neither aromatic or anti. Okay, anybody get an answer to this one? Aromatic, anti-aromatic?
Non-aromatic. I just put non-aromatic because it's so big. I built it and it was, I mean, my model didn't like being planar.
You built a model of it?
I did.
And it was not planar?
It could be.
It could be.
Well,
what about Huckel's rule? What does Huckel's rule tell you on this one?
That it would be by Huckel's rule.
It would?
It would be it would be aromatic by Huckel's rule.
2, 4, 6, 8, 10. Is every p orbital conjugated, at least on paper? Could, yeah. 10 is a 4n plus 2 number, right? Should be aromatic. If planar. Okay? Aromatic. If planar. I'm not going to write that every time, but that applies to every assignment we make, right? Okay. So how do we know if it's indeed aromatic? What kind of experiments would you run on it? NMR, look for where these H signals are. Alkene region or aromatic region? Heat of hydrogenation. Does it hydrogenate as if it's just 5 alkenes? Or does it have some aromatic stability? That is, you get much less energy out than you expect. Just some aromatic stabilization. Any other experiment you'd run on it? I mean, here it is. What would you do? Just look at it? No, you can't just look at it, right? Obviously, duh. What other data would you collect on it to tell me if it's aromatic or non-aromatic? Because would you expect it to be anti-aromatic?
No.
No. No, it's either aromatic or non.
Would it show up in IR with the mountain range if it was aromatic?
Yeah, that's something we didn't talk about here, but that's another, yeah. You'd have to see if that could give you help. Okay? I'm pretty sure that the answer is it's indeed aromatic, which implies it's indeed a planar compound. That compound is known to be aromatic. Okay? How about the next one? Every atom in the p orbital. Actually, these 2 are constitutional isomers, right? Same formula. What's the difference? Here, every alkene is cis or trans. All cis. What's the difference over here? Cis, cis, cis. It's got 2 trans. That's the only difference. Otherwise, it's still, how many pi electrons in this second one? 10. 4 plus 2 is 10. Okay, where n is 2. So Hochul's rule predicts aromatic if planar. Okay. What type of data would you collect? We've already went through that. Well, the answer is it's actually, guess what? It's actually non-aromatic, which implies what?
It's not planar.
It's not planar. Now, would a compound want to avoid being aromatic? No. Why is it not planar then? Well, it must be something to do with the trans, two trans bonds. But the reason is, if you draw in these H's here, right? Just look at the double bond. Boom, boom, right? Trans H's. There's one. Where's the other one? And guess what? The clash of those 2 little tiny H's makes this ring system go boop, and breaks the overlap and breaks the aromaticity. Steric clash. It doesn't want to do that, but apparently it has to. The clash of the 2 H's makes it do that. And that compound is known to exhibit non-aromatic properties. It does not exhibit aromatic properties. Which sort of tells us that it's not planar. And that's the reason why. The sterics breaks the planarity, okay? Yeah? Now, the original question was, how are you going to tell that on the test? Well, you ain't, because this compound is aromatic if planar. Everybody agree it's aromatic if planar? So maybe that's your answer, okay? You got to understand that it's, Hochul's rule is based on if it's planar. Okay? Naphthalene. Naphthalene is not a constitutional isomer. It has 2 less H's. To get the naphthalene, remove these 2 H's and instead bond these 2 carbons together. Okay? Remove H, and that would give that. And that compound is called naphthalene. It looks like 2 benzene rings fused together. And we have sides joining each other. It's called naphthalene. It's actually used as mothballs. There's 2 chemicals that are used as mothballs. If you go to Walmart, usually it's going to be dichlorobenzene. But naphthalene is known to be aromatic. Okay. Because whenever you have this here, just ignore an internal bond like that. Okay, just ignore that. Just count around the outside. Is every p orbital in the outside ring, does every carbon atom in the outside ring have a p orbital? Yes. How many pi electrons? 2, 4, 6, 8, 10. That's a 4n plus 2 number. We expect aromatic. Okay. So when you have bonds between the ring carbons, just ignore that bond. Sometimes you may have multiples. Okay? Just ignore those types of bonds. And count or look at the periphery as if that was not there. Okay? So we had one that was actually non-aromatic. That's actually like cyclooctatetraene, non-aromatic. Okay, let's look at some ions. Okay, this compound here, aromatic, anti-aromatic, or non-aromatic? Why not? Why is that?
It doesn't bond 4 and plus 2.
Well, I see 4 pi electrons. That's a 4n number with n is 1.
It's not it's not conjugated.
That's the answer, yes. There's no p orbital there. That's an sp3 tetrahedral carbon, no p orbital, right? Okay, non-aromatic. Just like ethanol or cyclohexane or, okay. But what about this one over here? What if we make that a carbanion? We can remove an H in acid-base chemistry, leave a lone pair behind. We can actually make such. Okay. What about it? Well, it's actually aromatic. Okay. Because what type of orbital is this lone pair in? What have we always said since the early inorganic one? Anytime a lone pair is next to a p orbital, you're going to want to be in a p orbital. Okay? P orbitals. Can you draw the pi system? Isn't that overlap, overlap, pi bond? Overlap, overlap, pi bond. And guess what? Can these overlap? Yeah. Okay, I'm not going to. Well, guess what? We put this one in a p orbital. And now what do you have? Every atom now has a p orbital all the way around. And they can interact. How many pi electrons in that system?
6.
2, 4, and lone pair makes 6. Can we do an MO diagram real quick of that? MO diagrams. We're not going to draw the actual pi system. By the way, we can look at we drew the MOs last time. It's actually a very good diagram of those MOs here. For benzene. MOs for benzene. Look at this. What was the lowest MO of benzene?
No.
Plus, plus, plus all the way around. Continuous overlap all the way around. See, this is showing electron density. See how the electron density is all the way around? Then when you go up, how many nodes when you go up one level?
1.
One node. See how you have electron density here and here, but then there's a node through here? So there's no electron density. One node. 2 nodes here. Okay? That's one molecular orbital. Can you rationalize? Imagine if there were 2 electrons sitting in this orbital. 4 different regions and 2 electrons are just there. How is that so? It's bad enough when you look at p orbital. And you say there's 1 electron in the p orbital. There's a node here. There's no electron. Is half the electron here and half the electron here? That's okay. Imagine this. This has four electron regions within that orbital. It's largely a lot of math. Okay? And that's mind-boggling stuff. You know, this is nice. 2 electrons here. It's like, okay, I can understand this. But on the ground state, isn't there 2 electrons here and 2 electrons here in benzene? No. Anyway, this is sort of a top view, and you can really see the nodes. This is the 6 MOs of benzene we drew last time. Okay. And by the way, there's also free information. Okay, no extra charge for this. Keep drawing MO diagrams. Okay. And we followed a lot of those rules when we did MO for benzene. Let's do an MO for this one. There's always going to be 1 at the bottom. That's where this can go to overlap all the way around. And then what? What do we say after 1 at the bottom? 2, 2, 2. How many p orbitals do we have in this compound?
6.
5. 1, 2, 3, 4, 5. Is there 1 at the top? No. 5 p orbitals leads to 5 MOs. Where's the midline? Oh. You draw it right through here, you have 1 below and 2 above. The midline is actually not number of MOs. divided. It's actually energy divided. The midline is actually through here. Of course, this is energy, right? How many electrons in the system? 6? 1, 2, 3, 4, 5, 6. All electrons paired, but that's what Hochul told us, because it's a 4n plus 2 number. This is bonding MO. What type of MOs are these? Since I drew them below the midline? Bonding, anti-bonding. Okay. When you have an odd number of MOs, finding the midline is more difficult. Also in the handout, it talks about the bottom of the key to drawing MOs. It talks about the frost mnemonic. You know, benzene, if you actually draw benzene with the point down and make each carbon a line, you'll actually get, now these, my bond is just a little bit longer, okay? You'll actually get the MO set up, 1, 2, 2, 1. And the midline, it cuts right through there. And that's the, look at the MO of benzene, that's, okay? You can do that with these compounds. Now this one here, it's all how you draw it. But usually these are drawn see, I'm not drawing it right. If you draw it, you'll see that the midline comes through here. 1, 2, 1, 2, 2. 1, 2, 2. With the midline above the 2 carbons. Okay. So this is an aromatic Anna. So ions can also be aromatic. And this anion, even though it's just a carbanion, usually those are difficult to form. This one is relatively easy to form. I'm just going to say H. One of the H's here is relatively acidic. Okay? Not that acidic, but it's much more acidic than just a regular hydrocarbon. What about the one on the right? If the lone pair was in a p orbital, this would be how many pi electrons? 2, 4, 6. Put this in a p orbital, it'll be 8. And what's the answer? Aromatic? Anti? Okay, anti-aromatic. If planar, right? You think it wants to be planar?
No.
Probably not. Can it avoid? How could it avoid being planar? How could it avoid being anti-aromatic?
Can it just bend itself?
What if instead of this being moving to a p orbital, what if it stayed just sp3? Remember how we said we always lone pair in a p orbital? And several times I would say, it's always good, unless it's bad. That's probably sp3. So it can avoid being anti-aromatic. Yeah? Again, there's actually very few anti-aromatic compounds in the world. Okay, how about the larger ring here? What is this, 7? Answer here? Non-aromatic. No p orbital there. sp3. How about the carbocation? What's the hybridization over here? Is there a p orbital over here? If you remember in organic 2, we graphed carbocations in late August. And we saw they had an empty p orbital, right? Yeah? Yeah. An empty p orbital. But aren't these also p orbitals? Knowing that there's a p orbital there, even though it's empty, it's there. Now you could argue about that. I would have to sit down for that argument. But me telling you it's there. Now, does every atom in the ring have a p orbital?
Yes.
Yes. Okay. Fully cyclic conjugated? Yes. How many pi electrons? 2, 4, 6, and none. 6. What type of number is that?
4 plus 2.
4 and plus 2, where n is 1. That compound should be aromatic if planar. Indeed it is. This compound, that carbocation, is aromatic. So how easy is it to form that carbocation? Relatively easy. Yes. Relatively easy to form. How about this over here? What do you want to say for this one? How many pi electrons? We assume the carbocation is 4. Yeah. What's the answer over here? Is this cation, is this carbocation aromatic?
No.
No, certainly not aromatic. Is it anti-aromatic?
If planar.
If planar. I think that one is probably anti-aromatic. We won't go any further than that. Can it avoid being anti-aromatic? I'm not sure. But here's a bigger type of question. Which carbocation is easier to form? This one or that one? Okay, you see how that, okay, we can have some easy questions. Because the polarity thing here is a little bit, okay. Everything we say for these aromatic or anti, if planar. So these two over here, were they easy to form? Oh, those two are very hard to form. Our understanding of aromaticity helps us understand the difference in the two carbocations and the two carbanions. Okay, we talked about the acidity of the top left up there. It's turned up. These H's actually have a pK of about 16. Usually hydrocarbon like this is like 30 or 40. Why so much more acidic? Well, we explained at the top. Because when a base takes the H, just going to use hydroxide, right? We take the H, leave the electrons behind. What are we forming?
An aromatic compound.
The aromatic carbanion. And it's very willing to form. That's why the H is acidic, relatively acidic. This is about the same pKa as water or alcohol. Okay, but see, those much less acidic because this would lead to top right. Not good. You can also see this in reaction mechanisms. Converting the OH to a Br, substitution. Why is the reaction on the left so much easier? What is the mechanism? Protonate, and then water leaves to make what, a carbocation? What type of carbocation would be formed over here? Aromatic carbocation. What's the rate determining step of these reactions usually? Forming the carbocation. This carbocation is going to form relatively easy. What about this carbocation? Imagine the carbocation there. We looked at it. It would not be aromatic. It would likely be anti-aromatic, if planar. And so there we see an aromatic intermediate enhancing the reaction rate. Make sense? Questions? What about compounds with heteroatoms? Pyridine, we've used it as a base. Tosyl chloride pyridine, often used as a weak base. It's just benzene with a CH replaced with a nitrogen. It's pretty good. It's a versatile weak base. Sometimes used as a solvent. Problem is, you remember benzene was carcinogenic? Pyridine's even worse. In particular, testicular cancer. Some of you don't have to worry about that. But it's known to be called testicular cancer. So you have to be careful with it. It's still very common around the lab. Actually, during the 8-week lab, I prefer to use lutidine, you'll see. It has methyl groups on it. With the methyl groups, like toluene has a methyl group on the benzene, nomenclature, by the way, like 7 to learn video. The methyl group, the body can oxidize it to carboxylic acid, and then the body can eliminate that molecule. That's why toluene is much less toxic than benzene. And if you put a methyl on pyridine, or 2 methyls, it decreases the toxicity. Okay. So is pyridine aromatic, anti-aromatic, or non-aromatic? Now, since we use it a good bit, it's probably not anti-aromatic, because those compounds are quite unstable. But what's the answer here? Basically, what's the hybridization of this nitrogen, and what type of orbital is the lone pair in? What type of orbital is the lone pair?
SP2.
Not an
It's
P orbital. It's SP2. I actually probably had you graph something like this back in August and September. Why? Because I knew today was coming. And you need to understand such. Okay? If you graph this, you will see that it's SP2. And the lone pair is in a hybrid SP2. The P orbital is being used to make pi bond. Should we graph it real quick? Now, you guys that did not have me for organic 1 probably did not graph as much as I did, but if you graph this, it's SP2. That means you got 3 hybrids, right? P left over. What type of bonds do you see this nitrogen making? Sigma bond to carbon here, sigma bond to carbon over there. What else? Pi bond to carbon over there. And what type of orbital do you use to make pi bond? Yes. And what is that all together? Double bond to carbon, single bond to carbon. Where's the lone pair? Okay, it's an sp2 hybrid. So, do we count this lone pair in an aromaticity discussion? No, that's only lone pair in p orbitals, electrons in p orbitals. No, forget about it. That's it, 2, 4, 6. It's just like benzene. That lone pair is not involved in the aromaticity. Forget about it. Forget that it's a nitrogen. It doesn't matter what it is. Just act like it's carbon there. Does every atom in the ring have a p orbital? Yes. How many pi electrons do you see? 6. That's 4 plus 2 is 1. Or N is 1. It's a helpful aromatic, right? Pyridine is aromatic. This shows pyridine over here, yeah? If you turn it to its side, that's the nitrogen there. Okay? The lone pair is sticking out with the sigma framework. If that was a carbon, it'd be an H sticking out here. Okay? So you can look at that. I know you can't look at it in 5 seconds and understand it. You got to look at it after class. All right? I'm just telling you what it is. Depiction of it. This compound down here is another nitrogen heterocycle called pyrrole. Okay, basic. Is it how you spell weekly? I reckon. Pyrrole. What about this nitrogen? It's got a lone pair.
That's a fuel.
This lone pair is in what type of orbital? P orbital. Why? Because any time a lone pair is next to a p orbital, I want to be in a p orbital. All 4 carbons have p orbitals. That's them there. And in this case, what's in the nitrogen p orbital? Lone pair. And so now we have overlap all the way around. Becomes one system. How many electrons? 2. There's 1 here, 1 here, 1 here, 1 here, right? How many electrons? 6. Okay. Aromatic. But the difference is, this lone pair is, the nitrogen is non-basic. Because what have we always said about a lone pair and a p orbital? The lone pair of a nitrogen is a p orbital, it's not going to be basic. Okay? A lot of this is review. All right? When I teach hybridization in August and September, Organic 1, I've got all this in my mind, trying to get you to this point. Okay? And it's the same things we did back in August and September, or whatever you guys did. Okay? Trust your hybridization knowledge. All right? These are 2 standard types of nitrogens in heterocycles. This is a pyridine type nitrogen. The lone pair is actually weakly basic. It is sp2. An sp3 lone pair is a little bit more basic than nitrogen. Okay. Where pyrrole, the nitrogen is non-basic because the lone pair is involved in the aromaticity. This is an imidazole. 2 nitrogens. But it's the 2 types of nitrogens you saw up there. That's a pyridine type nitrogen. Double bonded, lone pair in a what type of orbital? sp2. And this one is in p. Aromatic. How many pi electrons? 2, 4, 6. Not this one. Okay? Aromatic. 2, 4, 6. P orbital. 2 types of nitrogens to know how to deal with. Which nitrogen is basic? The upper one. Slightly basic. This amino acid is in the, this compound is in the amino acid known as histidine. You familiar with histidine? Learn your amino acids in some class. Some of them are considered basic amino acids because the side chain is basic. Why is the side chain of histidine basic? It's got a slightly basic nitrogen. It has an imidazole ring. Some drugs have imidazoles. This is midazolam, Versed, brand name, similar to Valium. It's got 4 rings. Benzene, benzene. We're not going to be able to name that one. But what's the name of this ring? A imidazole ring. Okay, and this nitrogen is basic. Question?
Would the nitrogen also be basic? Not the bottom one. Would the bottom nitrogen also be basic?
Yes, it actually would be, because that's a pyridine type nitrogen. Yeah? Both of those are slightly basic. What about that one? No. Not only is it conjugated in the ring to be aromatic, it's also conjugated with the benzene ring. Because there's a p orbital here. Yes, with any type of heterocycle, there's only going to be 2 types of nitrogens. And you recognize that the lower one was one type, and that the lower one is a pyridine type nitrogen. Okay, what about compounds with oxygen or boron or something? This compound is called furan. I've done a good amount of work with these 5-membered ring heterocycles, furan, role. This is called thiophene. Thio is sort of meaning sulfur. Aromatic? Anti-aromatic? 2 lone pairs, right? How many pi electrons here?
There are 8, 2, 4, 6. Are they?
No. What hybridization do you expect for the oxygen? Anytime a lone pair is next to a p orbital, we're going to want to be in a p orbital. It's sp2. We graph that. sp2, 1, 2, 3, p orbital left over. What type of bonds do you see the oxygen making? Sigma bond to carbon, sigma bond to carbon. Where are the 2 lone pairs? One of them is in a p orbital, the other one is in a hybrid. Which one how many do we count for aromaticity? Only p orbitals. Okay? It's just one. Okay? And then you got 4 more. 2, 4, 6, aromatic. Diphene is the same exact thing. Okay? Both of these are aromatic. 6 pi electrons. It's a lot like parole. We had 1 lone pair in the p orbital. But see, parole coming out here in the plane is a bond to H. Because it only has 1 electron, it has to make a bond. But with these, it has another lone pair. And so coming out here is a lone pair, just in that region, that hybrid region. What about borol, it's called? Hybridization of the boron. First question is, does the boron have a lone pair?
No.
Good, it does not. It only has 3 valence electrons. There's no lone pair there. Because if there was a lone pair there, the charge would be 2 minus. And since I'm not showing a charge, it must be neutral. There's no lone pair. 4 p orbitals here. What's the hybridization of the boron? 3 regions. What do you expect for 3 regions? sp2. Okay? It's going to have a p orbital. What's in the p orbital? Nothing. Empty p orbital. I mean, you can draw these in or not. I'll do it real quick. Right? Pi bond there. Pi bond there. But guess what? Those are interacting too. These are interacting. Okay? Once it all becomes interacting, that's no longer an empty orbital. We now move to there's just molecular orbitals there. And all that craziness takes over. And 2 electrons are in an MO all the way around there. It becomes one system once it's all conjugated. If aromatic. Problem is, what is the answer there? How many pi electrons? What's the answer? Anti-aromatic. I don't know anything about that compound really. I don't know if it's known to exist. It's certainly not aromatic. I don't know its properties. It might be non-aromatic for some reason. But theory would suggest it should be anti-aromatic, certainly not aromatic. Just need to understand the structure and hybridization of the boron. Also aluminum. Boron and aluminum will be identical. Question?
How can we identify an empty orbital?
Well, again, go back to August and September. Graph the hybridization of boron. I could actually do that back then. First thing is, how many regions around the boron?
3.
And 3, you expect what? sp2, right? And so you got sp2. That's 3 hybrids. And what else is there? The orbital. What type of bonds do you see the boron making? Sigma bond to carbon, and sigma bond to H. Okay, what's in the p orbital? It's empty. There's no lone pair there. This is isoelectronic to that there. Isoelectronic, same electronic sort of configuration. Wasn't that an empty p orbital? If you get rid of the charge and change it to boron, there's an H, there's an undrawn H here, okay? Right? There's an undrawn H there. Get rid of the charge, change that to boron, and draw in the H. The rest of the discussion is the same thing. See, boron has 1 electron. If carbon has the same number of electrons, it'll be missing 1 and must be positive. But with boron with that number, it's not positive, it's neutral. One last thing I want to say here down here is both of these are aromatic. Which one might be more aromatic? Now we're not really going there, but I'll just ask anyway. Is there a way to?
Would oxygen, because it's less, no?
Well, tell me about oxygen.
It's super greedy, super electronegative.
Okay, so how delocalized are these electrons? Is the oxygen really willing to let them be sort of fully delocalized through here? Yeah, not as much. Oxygen wants to be greedy and just hold them. I don't want to play this aromaticity game, the oxygen says. Yeah. Sulfur more willing. So that's an argument there. What's an argument for making this less aromatic? Okay. Any argument over here?
The sulfur can expand its octet, so it has the potential to overthrow to mess up the electron count.
I'd have to see what you're talking about. But one thing that you guys often don't point out is when we do p orbitals, and don't do this like that. But when we do these over here, what did I just do?
It's a lot bigger.
The sulfur is in a, it's in the bigger shell. The p orbital is bigger. And that lone pair here, what is that going to do to the overlap? We're out of time here. But when things overlap, it's like full, all these electrons overlapping. What if instead you want to overlap this with this? It doesn't overlap as well. So that's one consideration. Okay. We can pick up here. We'll be moving into reactions, guys, on Friday, and I gave you those 2 handouts today. See some of you in lab tomorrow upstairs.